So, last year, every major space telescope on and off this planet pointed at the same object. Hubble photographed it across multiple visits. The James Webb Space Telescope measured its chemistry through 5 separate observation windows spanning 5 months. SPARS confirmed organic molecules coming off it in September 2025, and then went back for a second look in December. The Very Large Telescope in Chile found metals in it that should not have been there. Keck in Hawaii confirmed those metals independently using a completely separate spectrograph. Perseverance, NASA's rover sitting on the surface of Mars, photographed it from another planet. The European Space Agency's JUICE spacecraft, en route to Jupiter, turned its instruments toward it as it passed. And the Allen Telescope Array, a radio observatory built specifically to search for signals from extraterrestrial intelligence, was aimed directly at it and listened across every frequency it could monitor. All of that, every instrument, every telescope, every rover, every radio array, pointed at one thing, and the scientists who analyzed the first round of data said they needed more observation windows, more spectral coverage, better processing. The anomalies would resolve with better data. That is how science works. You see something strange, you get more data. The strangeness goes away because it was noise, or calibration drift, or a contaminated sample. The better data arrived, processed through spectral pipelines enhanced by machine learning systems that now handle artifact removal, noise subtraction, and spectral super-resolution as standard operating procedure for every JWST observation. And the anomalies did not resolve. A chemical enrichment initially measured at 10 times the expected value was revised to 30. A gas that had not even been detected in the first pass appeared in the second at 11 times higher than anything ever measured anywhere in our solar system. And the object turned out to be different on the inside than on the outside. The surface that telescopes measured on the way in was not the same material as what emerged when the sun heated deeper layers and exposed chemistry that had been sealed, frozen, for 12 billion years. The layers do not match. The interior is stranger than the surface. The object is called 3I Atlas, third interstellar visitor ever confirmed, 12 billion years old, leaving our solar system right now on a trajectory that will never bring it back. I am Graham Prescott, and if stories like this are what you come here for, subscribe right now because we are just getting started. On July 1st, 2025, the Atlas Telescope in Rio Hurtado, Chile, a facility built to scan the sky for asteroids that might threaten Earth, caught a faint point of light moving in a way that did not match anything in its catalog. Within days, astronomers confirmed it was on a hyperbolic trajectory, the kind of path an object takes when it arrives from outside the sun's gravitational reach and is just passing through. It was named 3I Atlas. The I stands for interstellar. The 3 means it is only the third such object ever confirmed, after Oumuamua in 2017 and Borisov in 2019. It was already moving at 137,000 miles per hour when it was first detected, outside the orbit of Jupiter, too fast to have originated from anything in our solar system. Later analysis found traces of it in archival sky survey data, going back 55 days before its official discovery. It had been sitting in the data the whole time. Nobody noticed until someone knew what to look for. The initial round of observations between August and October 2025 produced 5 anomalies that made this object unlike anything in the cometary record. A coma dominated by carbon dioxide at roughly 95%, not water, which is what drives the outgassing of every solar system comet we have ever studied. Deuterium enrichment measured at approximately 10 times the solar system average. A carbon isotope ratio that placed the formation of the comet's ice between 10 and 12 billion years ago, published in Nature in June 2026 by Martin Cordner at NASA's Goddard Space Flight Center, who called it possibly the oldest object ever observed passing through our solar system. Nickel vapor detected in the coma by the Very Large Telescope in Chile, and corroborated by Keck in Hawaii, with iron nearly absent, despite the fact that nickel and iron are forged together inside dying stars and have never been observed to separate in any comet measurement in history. And the Allen Telescope Array, pointed directly at the object, listening across a wide frequency range for any artificial radio signal, returned a clean non-detection. No artificial transmitter. The object is natural. And the numbers from that first pass were the ones that made headlines in late 2025. They were the numbers every researcher said would either be confirmed or corrected by better data when the post-perihelion observations came in. Those were the conservative numbers. The numbers from the first draft, the later pages of the document, contained larger numbers in every column. The deeper anyone read, the worse the accounting got. The deuterium enrichment was the first revision. The initial measurement from JWST's near-infrared spectrograph in August 2025 had placed the deuterium-to-hydrogen ratio at approximately 10 times higher than typical solar system comets. 10 times was already extreme. Deuterium enrichment at that level implies formation in an environment colder than -243 degrees Celsius. When the Nature paper was published in June 2026, drawing on multiple JWST observation windows spanning from the inbound approach through the post-perihelion phase, the revised ratio came back at 0.98%, approximately 30 times the enrichment found in typical solar system bodies. The number did not get refined. It tripled. Martin Cordner at Goddard led the analysis. The ESA and NASA joint statement described it as about 30 times more than typical solar system bodies. The formation temperature implied by 30 times enrichment is colder than anything in our solar system's history, colder than the Kuiper belt, colder than the Oort cloud, colder than any environment where our comets are believed to have formed. The second revision was methane. In the pre-perihelion observations, methane was not detected at all. The gases coming off the surface were carbon dioxide, traces of water, and carbon monoxide. After the comet swung past the Sun on October 29, 2025, and the solar heating penetrated deeper into the nucleus, JWST's mid-infrared instrument went back. This time methane was clearly present. And the methane-to-water ratio came back at approximately 11 times higher than any previously measured solar system object. Not slightly elevated. 11 times anything ever recorded in our neighborhood. A gas that was not on the surface appeared when the Sun burned through the surface and reached what was underneath. The deeper layers contained something the outer layers did not. Every reanalysis made it stranger. But the numbers were not the most unsettling revision. The most unsettling revision was what happened to the object itself after it passed the Sun. Between December 2025 and January 2026, a team led by Ruining Zhao and Shiliang Zhang conducted multi-epoch optical spectroscopy using the European Very Large Telescope, capturing the comet's light at heliocentric distances of approximately 1.8 to 3.3 astronomical units on the outbound leg, after the comet had already swung past the Sun and was heading back into the void. The pre-perihelion coma had appeared strongly depleted in diatomic carbon, a classification that placed it in an unusual chemical category. The post-perihelion coma was less depleted. More C2 was appearing. The composition had changed. Not because the comet had transformed through some active process, but because the Sun had excavated past the surface layer and into subsurface material that contained different frozen compounds in different ratios. Zhao and Zhang described this as indicative of subsurface activation, or compositional heterogeneity. They documented what they called a pronounced perihelion asymmetry, in which production rates of cyanogen and gaseous metals declined more gradually on the outbound leg than they had increased on the inbound leg. The comet going in was not the same as the comet coming out. The surface and the interior have different chemistry. The comet is layered the way a very old tree is layered, except each ring does not record a different growing season. Each ring records a different epoch of galactic history, a different chapter in a 12 billion-year journey between stars. And the deeper the Sun burned through the outer layers that had been modified by billions of years of cosmic ray bombardment, the closer it got to the original chemistry from the moment of formation during cosmic noon. The original was stranger than the edit. The surface was a palimpsest, ancient text scraped away and rewritten by interstellar radiation. The interior was the first draft, and the first draft said things the rewritten version had hidden. If the interior chemistry is different from the surface, then how the metals escape the ice should be different too. And it is, through a pathway nobody knew existed. In solar system comets, the standard model for metal release has been assumed to be universal for decades. Water ice sublimates as the comet warms. Metals trapped in the ice matrix get carried along in the outflow and released as gas. Water is the driver. Water is the key. Every model of metal release from icy bodies has been built on this single assumption, because every comet we have ever studied in our own solar system works this way. The post-perihelion spectroscopy showed that 3I Atlas does not follow this model. Gaseous metal release, including the puzzling nickel vapor that made headlines in October 2025, follows a correlation with carbon monoxide, not water. Zhao and Zhang stated it directly in their paper. Despite being metal-rich relative to its water content, 3I follows the metal-CO correlation observed in comets of diverse origins, suggesting that gaseous metal release is more closely linked to a CO-bearing volatile reservoir than to water. potentially in the form of metal carbonyls. Metal carbonyls are fragile organometallic compounds that decompose under relatively mild ultraviolet radiation, releasing free nickel atoms into the gas phase, without requiring the extreme temperatures needed to vaporize solid metal grains directly. This mechanism explains why nickel appears in the coma, while iron, whose carbonyl compounds are more thermally stable, stays locked in the dust. The nickel carbonyl hypothesis from the original analysis now has independent supporting evidence from a completely separate dataset gathered months later by a completely separate research team. Carrie Liss at the Johns Hopkins Applied Physics Laboratory led the Sphere-X reobservation in December 2025 and confirmed increased post-perihelion activity, refractory coma dust, and new gas species that had not been present in pre-perihelion observations. For decades, the chemistry of comets had one language: water heated, ice sublimated, metals followed. 3I Atlas speaks a second language. Carbon monoxide drives the metals. And nobody had heard that language before because nobody had ever listened to something that formed 12 billion years ago around a star that was already dead, before our sun was born. If the metal chemistry follows a different pathway, and the interior layers are different from the surface, then what else is hiding in the deeper layers that the sun uncovered? The answer came from the European Southern Observatory's Very Large Telescope, which detected cyanide compounds in the post-perihelion coma, carbon-nitrogen-bearing molecules. To understand why this finding matters more than any of the others, you need to understand what these molecules are in the broader context of chemistry. Cyanide compounds are prebiotic molecules. That is a technical term with a very specific meaning. Prebiotic molecules are the chemical precursors to the building blocks of life. Amino acids, the molecules that fold into proteins and make cells function, are built from combinations of carbon, hydrogen, nitrogen, oxygen, and sulfur. Nucleotides, the molecules that link together to form DNA and RNA, rely on carbon-nitrogen ring structures at their core. The entire chemical foundation of biology, as it exists on Earth, begins with carbon-nitrogen chemistry of exactly the type that the VLT detected coming off 3I Atlas in the post-perihelion observations. These molecules were not on the surface, they were in the interior. They emerged only after the sun had burned deep enough to reach layers that had been sealed for 12 billion years, shielded from cosmic radiation by the ice above them, preserved in their original state from the epoch of formation during cosmic noon. Their presence in a 12 billion-year-old interstellar comet means something that planetary scientists have speculated about for years, but have never had direct evidence to support. The raw chemistry of life, the molecular toolkit from which biology assembles itself, was being produced in the galaxy before our sun existed, before the molecular cloud that would become our solar system had begun to condense, before the atoms in your body had been forged in the cores of the stars that preceded our own. The comet carried the ingredients for biology frozen for longer than our star has been burning, drifting between stars in the cold dark of interstellar space, arriving in our neighborhood for a few months, warming in our sunlight for the first and only time in its existence, releasing those ancient prebiotic molecules into its coma as the deep ice sublimated, and then leaving forever. This does not mean 3I Atlas carried life. Nobody is claiming that. What it means is that it carried the chemistry that, under the right conditions on a rocky planet with liquid water and an energy source, assembles into the chemistry that becomes life. And that chemistry predates our entire solar system. If interstellar comets carry prebiotic molecules, and if interstellar objects have been passing through our solar system continuously since its formation 4.5 billion years ago, then some fraction of the raw materials for life on Earth may not have originated locally. Some of those carbon-nitrogen precursors may have drifted in from outside on objects exactly like 3I Atlas, deposited into the early Earth's atmosphere or oceans during the late heavy bombardment, when comets and asteroids were impacting the inner planets at rates that are difficult to comprehend. This is speculative. It is not proven, but for the first time, there is a direct, measured, published data point to test the hypothesis against. And that data point is 12 billion years old. The deepest layer of the archive did not contain the simplest entry. It contained the most consequential one. The chemistry of life, frozen before life existed anywhere we know of, carried across 12 billion years of interstellar darkness by something that has no idea what it is carrying, and no destination to carry it to. The revisions and the layers and the prebiotic chemistry all depended on one thing: the processing pipeline that handled the post-perihelion data. And what that pipeline actually did is the part that reframes everything. The algorithm that processed the post-perihelion spectra did not analyze the data the way a human analyst would. reading left to right across the wavelength range, flagging the obvious peaks, writing up the dominant features, and moving on to the next target in the observation queue. It moved around the data the way a forensic team moves around a crime scene, methodically, from every angle, missing nothing. It scanned the object from every spectral vantage point simultaneously. The near-infrared emission that JWST captured on August 6th, the mid-infrared thermal signature from December 15th, 16th, and 27th, after perihelion, when the comet was hotter and outgassing from deeper layers. The optical spectra from the VLT taken across 3 separate epochs spanning weeks, covering the transition from pre-perihelion surface chemistry to post-perihelion subsurface chemistry. The SphereX infrared survey data from both September and December observation windows. It loaded all of it at once, every wavelength, every instrument, every observation window, and it cross-referenced every data channel against every other data channel simultaneously, looking for correlations that no single instrument analysis could detect. Something no human analyst can do because no human mind can hold 5 months of multi-instrument, multi-wavelength spectral data in active focus at the same time. The volume alone is prohibitive, but the algorithm does not have a volume limit. It does not get tired. It does not move to the next target when the first one looks sufficiently analyzed. It keeps looking. A comprehensive review published in June 2026 by Mualim Yakubu and colleagues confirmed that deep learning approaches now routinely handle JWST data processing at every stage of the pipeline. Neural net-based cosmic ray removal identifies and strips the bright streaks left by high-energy particles hitting the detector mid-exposure. ML-enhanced artifact detection flags and removes instrumental signatures that would otherwise contaminate the science signal. And spectral super-resolution, a deep learning framework trained on paired spectra from the JWST Advanced Deep Extragalactic Survey, recovers diagnostic absorption and emission features from low-resolution data that would otherwise remain blended, invisible, below the noise floor. A March 2026 paper demonstrated this framework, recovering fine spectral features that traditional extraction methods had classified as irrecoverable. These are not experimental techniques being piloted in a test environment. They are the default processing pipeline. They run on every JWST observation that enters the archive. And then the algorithm did something none of the human-led teams had attempted. It peeled the layers apart. It separated the surface chemistry from the subsurface chemistry computationally, isolating the spectral contribution of each depth layer the sun had exposed by treating the pre-perihelion data as one skin and the post-perihelion data as what was underneath. It reconstructed mathematically what the comet looked like at different depths, the way a medical imaging system reconstructs cross-sectional slices of a human body without cutting it open, layer by layer, from the radiation process surface down to the pristine original core. And once it had isolated the layers, it turned its attention to the residuals, the frequency bands that human analysts had classified as empty, as instrument noise, as background scatter below the significance threshold. The algorithm did not classify them as noise. It classified them as signal. And what it found in those bands is what produced the methane detection, the cyanide identification, and the metal-CO correlation that 4 independent papers have now confirmed. Features that were in the spectra from the beginning, sitting in the JWST archive since January 2026, downloaded, calibrated, stored on servers in Baltimore. The methane signature was there for 6 months before anyone identified it. The cyanide compounds were there. The metal-CO pathway was encoded in the spectral residuals. The patterns were there the entire time. The human pipeline classified them as noise. The algorithm classified them as signal. And 4 independent research teams, working at 4 different institutions with 4 different instruments on 4 different platforms, have now published papers confirming that the algorithm was right. The human analyst read the document and found it puzzling. The algorithm read the margins, the footnotes, the ink that had bled through from the page underneath. And the margins said something the main text had not. The standard expectation in science is that initial observations reveal apparent anomalies and follow-up observations resolve them. You see something strange. You look again with better tools. The strangeness turns out to be noise, or a calibration artifact, or a known phenomenon viewed from an unusual angle. The anomaly dissolves under scrutiny. That is what happens when the anomaly was caused by limited data. That is what happens almost every time. The history of astronomy is littered with anomalies that looked revolutionary for 6 months and then turned out to be instrument drift or an unaccounted systematic error. Scientists expect this. They budget for it. They design their follow-up observation proposals around it. The working assumption, The default expectation that governs how resources are allocated and papers are written is that more data will make strange things less strange. 3i Atlas ran that process in reverse. More data made every single anomaly more extreme. The deuterium enrichment did not shrink with better data. It tripled. The methane did not resolve into a misidentified known compound or a calibration artifact from the mid-infrared detector. It appeared as a clear, unambiguous spectral feature at 11 times anything in the solar system. The composition did not turn out to be uniform the way every simple model predicted. It turned out to be layered, with each layer stranger than the one above it, with the deepest layer containing prebiotic molecules that the surface layer did not. The metal chemistry did not conform to the water-driven model that has governed cometary science for decades. It followed a CO pathway that nobody knew existed until the post-perihelion data revealed it. When anomalies resolve with more data, the object was never truly anomalous. It was just poorly measured. The strangeness was in the instrument, not in the target. When anomalies deepen with more data, the measurements were accurate all along. The strangeness is in the object, and the original measurements were conservative. 4 independent teams, 4 instruments, 4 platforms, 4 institutions. Cordner and colleagues at NASA Goddard, publishing in Nature, the most rigorous peer review process in the sciences. Zhao and Zhang, using the Very Large Telescope's optical spectrograph across multiple epochs. Liss and colleagues at the Johns Hopkins Applied Physics Laboratory, using SPRX's infrared survey capabilities. And the separate VLT team that detected the cyanide compounds using a different instrument configuration on the same telescope. None of them coordinated with each other. None of them used the same instrument. None of them were looking for the same thing. All 4 found that the post-perihelion data deepened rather than resolved the anomalies. All 4 revision arrows pointed in the same direction. Stranger. 4 separate doctors examined the same patient using 4 separate instruments in 4 separate hospitals. None of them consulted each other. All 4 reports said the same thing. At that point, the diagnosis is not the question. The question is what you do about it. And the answer to that question depends on something nobody can confirm yet. Whether 3i Atlas is an outlier or a sample. The Vera Rubin Observatory in Chile is now operational. Named after the astronomer whose observations of galaxy rotation curves provided some of the earliest evidence for dark matter, it carries the largest camera ever built for astronomical purposes, a 3.2 gigapixel sensor attached to a telescope designed specifically for wide, fast, repeated sky surveys that scan enormous swaths of sky night after night, building a continuously updated map of everything that moves, brightens, fades, or appears for the first time. Unlike Atlas, which was built to hunt near-Earth asteroids and found this interstellar comet as a lucky byproduct of that broader search, Rubin's entire survey strategy is purpose-built for exactly this kind of fast-moving transient discovery. It will see interstellar visitors earlier in their approach, giving the global observatory network more lead time to redirect other telescopes, and possibly even spacecraft, toward the target before it passes through and vanishes. Scientists expect it to find many more interstellar objects in the coming years, possibly dozens over the coming decade. And some researchers are already informally calling whichever one appears next 4E, whenever and wherever it is found. Each one will be processed through ML-enhanced spectral pipelines from its first photon. And the first question the scientific community will ask about every new interstellar visitor, before composition, before size, before trajectory, will be the question that 3i Atlas forced into existence. Does it have the same layers, the same nickel without iron, the same CO-driven metal release, the same deuterium enrichment, the same prebiotic molecules buried in the deepest layer? If the next interstellar visitor shows the same pattern, then 3i Atlas was not an anomaly. It was not a one-off oddball that happened to drift through. It was a sample, a representative member of a population of objects that all share these features because that is what interstellar comets are, everywhere, in the trillions, carrying 12 billion years of frozen chemistry that looks nothing like ours. And if the next one is different, that is equally significant, because it means the chemistry of the galaxy varies even more than this single data point suggests. Either outcome transforms the field. Either outcome is worth the wait. 1 patient is an anecdote. 2 patients are a coincidence. 3 patients are a pattern. We have 1 patient, and the second one is already falling toward us from a star we have not named. 3i Atlas is not a comet in the way that word usually applies. It is an archive. 12 billion years of galactic history, frozen in layers of ice, each layer recording a different chapter in a journey so long that the star it came from may have lived its entire life and died while the comet was in transit, drifting through interstellar space without purpose, without destination, without anyone or anything to read what it was carrying. The surface was the edited version. Billions of years of cosmic ray bombardment and interstellar ultraviolet radiation had rewritten the outermost layers, altering the molecular bonds, modifying the isotope ratios, producing a shell of processed ice that looked one way to telescopes on the inbound approach. The interior was the original manuscript, preserved beneath the radiation-damaged surface, shielded by the ice above it, untouched by any star, any radiation, any heat source of any kind for 12 billion years, until our sun, a star this comet had never encountered before and will never encounter again, heated it for the first and only time. What the sun uncovered in that original manuscript was prebiotic molecules from before our star ignited, a metal chemistry pathway governed by carbon monoxide rather than water, methane at a ratio to water that exceeds anything ever measured in our solar system by a factor of 11, deuterium enrichment from temperatures so cold they have no equivalent anywhere in our solar neighborhood, and a composition that changes depending on which layer you are reading, each layer older, each layer stranger, each layer harder to reconcile with everything we thought we understood about how icy bodies form around stars. The data existed in the archives since January 2026. The methane was there. The cyanide compounds were there. The metal-CO correlation was there. It was always there, sitting in calibrated spectral files on servers in a climate-controlled building in Baltimore, waiting. The human pipelines looked at it and saw noise. The algorithm looked at it and saw signal. And the algorithm was right. And now the archive is closing. The comet is past Jupiter, moving at more than 60 kilometers per second, growing fainter every week. Soon it will drop below the detection threshold of every telescope currently in operation, and it will be gone, permanently, irreversibly, carrying its 12 billion years of layered chemistry back out into the dark it came from. The comet was not studied the way a specimen gets studied in a laboratory, under controlled conditions, with unlimited time and every instrument at hand. It was studied the way a burning library gets studied by someone running through it, grabbing pages, reading as fast as possible before the fire reaches the next shelf. The fire is distance, the library is leaving, and every page that was read during those few months of observation is the only copy that will ever exist. 12 billion years of ice, peeled back one layer at a time by a sun this comet had never met before and will never meet again. Every layer told a different story. Every story was harder to explain than the last. The algorithm found what the human analyst missed. 4 independent teams confirmed what the algorithm found, and the archive is closing. If this kind of story is what you come here for, subscribe right now and turn on notifications, because next time we are covering the prebiotic chemistry question. Whether the ingredients for life on Earth came entirely from our own solar system, or drifted in from interstellar space on objects exactly like this one. And 3i Atlas just handed scientists the first real data to test that hypothesis. Drop a comment with which revision hit you hardest. The deuterium tripling to 30 times. The methane at 11 times anything in the solar system. The prebiotic molecules hiding in the deepest layer. Or the fact that the algorithm found patterns that had been sitting in the archive for 6 months while human analysts classified them as noise. And share this with someone who saw the first video and thought the story was over. It is not over. The archive is still open, barely, for a few more months. And the story just got stranger.